Welcome to the Deep Dive, where we take a pile of sources, rip them apart, and give you the essential knowledge.
Yeah.
Today, we are literally starting from the ground up. We're diving into the hidden structures, the frames beneath all the plaster and glass that hold up our world.
And this is one of those deep dives that it really changes how you see your environment.
How so?
You start to look at a building not just as, an object, but as an engineered solution. And our source today is, well, it's perfect for this.
Right.
It's a foundational textbook, Traditional Construction, written for Level 1 carpentry and joinery students by James Rix. He's an educator, a site professional.
That context is gold. It means we're getting the real ground-level truths that professionals need to know, not just academic theory.
Exactly.
So our mission today is to unpack the four traditional building frames: timber, concrete, steel, and masonry.
And then connect that to the UK classifications for building height.
Because, as we're going to see, that height changes everything. The rules, the safety, all of it.
Think of it as getting the technical blueprint for the city you live in.
I love that. Okay, let's unpack this. Let's start with the oldest, most crafted method. Traditional timber.
When we talk about traditional timber framing, we are going way back. We're talking about hundreds of years of construction history in the UK medieval era.
And this is a method defined by these huge, heavy wooden beams, right?
Yeah.
The whole skeleton is made of them.
It is. And crucially, this is not the stick framing you see on a modern housing development with lots of smaller pieces of wood.
No, this is massive, solid stuff. It must take some serious skill.
And that skill, it really shines in the joinery, the way it's all connected. This is what separates the traditional method from, modern engineered timber. They rely on joints called
Mortise and tenon.
mortise and tenon joints, exactly. The classic connection.
A tongue fitting into a socket, basically. But that seems so labor-intensive. I mean, why is that specific method still relevant?
Well, it's not just the shape of the joint, it's how they secure it. Today, we'd use metal plates, screws, nails. But traditional frames are held together with wooden pegs.
Wooden pegs. Why avoid metal? Is it just for the look, the tradition of it?
That's the fascinating part. It's actually a core engineering reason. Metal fasteners make everything rigid. They lock a joint solid.
Okay.
But a building, especially one made of wood, it needs to move, it settles, it expands and contracts with the weather. And that little bit of managed play you get from a wooden peg, it allows the whole structure to flex without breaking. It prevents stress fractures. It's engineered flexibility.
So it's strong because it can give a little. That's a great insight.
It's an anti-fragile design, really.
So once you have this huge wooden skeleton up, you have to fill in the gaps between the beams.
Right.
Historically, that was what? Wattle and daub?
Wattle and daub, or sometimes brick. Today, of course, you'd fill those panels with high-performance insulation to meet modern standards.
Of course.
But the core benefits are still there. It's strong, it's long-lasting, it's a renewable resource, and it gives a building just immense character.
Okay, so from that slow, skilled craft, let's jump forward, to the industrial era, to the materials that let us build up, not just out.
Concrete and steel.
Concrete and steel.
These two really did change the game. They gained huge popularity in the UK in the 20th century because they could do things structurally that wood just couldn't manage at that scale. Let's start with concrete frames.
Right. Concrete is everywhere. We think of it as incredibly strong. So why do we always hear the term reinforced concrete? What's its weak spot?
It all comes down to physics. Concrete is phenomenal under compression. You can push down on it all day.
Squeezing it.
Exactly. But it's terrible under tension. That's pulling, bending, stretching. So if you imagine a long horizontal beam, the top is being compressed.
So the bottom is being stretched apart.
And that's where unreinforced concrete would just crack and fail completely.
And that's where the steel comes in.
That's where the steel saves the day. You place steel bars, known as rebar, inside the concrete form before you pour. And those steel bars carry all the tensile load, all that stretching force, which makes the whole thing incredibly strong.
Can you walk us through that traditional pouring process, the in situ method? It sounds like a massive on-site operation.
It's very time-intensive. In situ just means on-site. So first, the builders construct this temporary mold, this box, out of timber.
That's the shuttering or formwork.
Right, and it has to be perfectly built and strong enough to hold tons of wet concrete. Then the steel rebar cage goes inside, and finally, you pour.
And then you have to wait days, weeks for it to cure before you can even start on the next floor up. That must be the big drawback.
It is, it's time, and that's why, we see this big modern shift towards precast concrete.
Where it's all made in a factory.
Exactly. Made in a factory under perfect conditions, shipped to the site, and just craned into place. Much, much faster.
That wet, slow process is such a contrast to our next material.
Okay.
Steel. Steel frames feel like the absolute peak of industrial efficiency.
They really are. With steel, you're creating a rigid but lightweight skeleton. If concrete is about mass and compression, steel is all about tension and spanning distance.
That ability to span huge distances without needing columns everywhere, that's the revolution of steel, isn't it?
Yeah.
It just changed what interior space could be.
It did. It's the reason we have the modern open-plan office, or a giant warehouse floor, or an arena with no columns blocking your view.
Right.
Steel is perfect for commercial buildings where you just need huge, flexible floor space.
And the building process is totally different from pouring concrete.
Completely. The steel beams and columns are made off-site to exact measurements. They arrive dry, ready to
But
go.
to bolt them together.
You bolt or weld them. The speed of assembly is incredible compared to concrete or masonry. It can slash construction time.
And from a sustainability perspective, steel also does pretty well.
It does. There's very little waste on site because it's all prefabricated. And steel is one of the most recycled materials on the planet.
Okay, so far we've got wood, concrete, and steel, and they all create a kind of skeleton, right? A frame that holds the weight and then you fill in the walls.
Correct.
But our last traditional method, masonry, it just flips that whole idea around.
It flips it completely. Masonry is the absolute staple of UK housing, and its core principle is that the walls themselves are load-bearing.
So if I'm looking at an old brick house, the weight of the roof and floors isn't on some hidden frame. It's coming right down through the bricks.
That's it. The walls are the structure. The strength comes from the pure mass and compression of the brick or block. And because it's so common in the UK, builders developed a really clever system for our damp climate.
The cavity wall.
The cavity wall.
Which you need because a single solid brick wall would be cold and let in moisture. Right?
Yeah, for sure. So a cavity wall has two layers or leaves. The inner leaf is the structural one, usually made of strong concrete blocks that carries the load.
And the outer leaf is the nice brick you see on the outside?
Right. That's for weather protection and the final look. And between them is the key, the cavity, an air gap.
And they're tied together somehow.
They are, with little stainless steel wall ties. But the gap is the important bit. It stops rain from getting through to the inner wall, and it acts as an insulating layer to keep heat in.
The textbook also points out two other big benefits of masonry, things homeowners really care about: acoustic performance and thermal mass.
Thermal mass is fantastic, and it's so often overlooked.
What is it exactly?
Just think of the brick walls as a giant heat sponge.
Okay.
They slowly absorb heat when the room is warm, and then they slowly release it back when it gets cool. It helps stabilize the temperature inside your house all year round.
And I guess that same density that holds heat also blocks sound.
It gives it fantastic acoustic performance. Quieter homes, better separation from the neighbors. It's why people value it for durability and comfort.
But there's a trade-off.
A big one. It's slow. You're laying one brick at a time. You need skilled bricklayers, and you can't work in bad weather. It's generally the slowest of all four methods.
And that slowness and the fact you can only build so high with load-bearing walls brings us right back to steel and concrete frames when we want to build tall.
Exactly.
Which gets us to the regulations. So we know what holds these buildings up, but how does the UK classify them? And so what? What does that mean for planning and safety?
It means everything. The choice of material is totally tied to the building's height, and that height dictates how much scrutiny it gets.
So the UK has sharp categories for this. Let's start at the bottom. Low-rise buildings.
Right. These are your typical structures with fewer than 5 stories, so 1 to 4 floors.
Most houses and small apartment blocks.
Yeah. And they're popular for a reason. They're cost-efficient, they're easier to maintain, and they fit into existing neighborhoods really well. They support that community feel.
But with housing pressure being what it is, especially in cities, there's that crucial next step up.
The mid-rise building. This is typically between 5 and 12 stories, and these are now seen as a really vital solution for urban density.
So a way to get more homes on the same patch of land without building a giant skyscraper.
Exactly. The source notes that London, historically, has favored sprawling low-rise housing, which is one reason land is so scarce and expensive. The mid-rise is seen as that perfect balance.
The sweet spot.
It is, but they often face planning hurdles. But once you go past that 12-story mark, everything changes.
You enter the world of the high-rise building.
And in the UK, that's officially a building with 12 or more stories that has at least 2 homes in it. And the moment it hits that definition, it is automatically classed as higher risk.
And that higher risk label comes from the Building Safety Act 2022.
A huge piece of legislation, a complete overhaul of the system.
So what does that higher risk classification actually trigger? What happens?
It triggers intense oversight from a new body, the Building Safety Regulator. The whole point of the act is to bake safety in from the very first sketch.
How do they enforce that?
Through a mandatory 3-gateway approval process.
Okay, let's break those down. What's the first gateway?
Gateway 1 is at the planning stage. Before you even get permission to build, you have to prove your fire safety and structural plans are solid.
So safety is no longer an afterthought. It's the first thing you have to solve.
The very first thing. Gateway 2 is before construction begins. The regulator has to sign off on all the detailed plans, the material choices, everything, ensuring it meets the absolute highest standards.
And the final one.
Gateway 3 is at completion. The regulator inspects the finished building to make sure it was built exactly as designed.
And people can't move in until it's signed off.
No one can occupy the building until it gets that final approval. It creates these crucial safety checkpoints at the beginning, middle, and end of the entire project.
It's amazing how the materials that allow us to build tall, the steel and concrete, have directly led to this incredibly rigorous set of rules to manage the risk.
It connects it all. The history, the materials, the policy. Now you can understand the solid integrity of a brick house, the engineered flex in an old timber barn, and the immense regulatory system that governs that skyscraper downtown.
That's the goal. You now have the code, really, to walk through any city and understand its logic, from medieval joints to modern safety gateways.
And this raises an important question, doesn't it? We've seen how a centuries-old idea, like the mortise and tenon joint, endures because it solves a fundamental problem. Movement. So what's the next material breakthrough we need? What new composite or, self-healing concrete will solve the modern problems of waste, speed, and the intense safety demands of the high-rise era?
Something to think about.
Something for you to consider the next time you look up at a crane over your city.